So now 7.7 is the application of the dot and cross product that we learned, in 7.3, 7.4, 7.5, all these different sections. And we can apply these to concepts in physics, but really it's a concept of vectors, right? So we can use the dot product to actually calculate work. And if you haven't taken physics yet, work is just a composition of force and displacement. So think of how much work something is. If you're dragging something, there's two components there. There is how much force you're dragging and the distance that you're dragging it, and that equals work. So here we have the formula for it. It's the force vector versus the displacement vector, where the force vector is force along the line of displacement, and this is just the displacement. Okay, and this is in newtons usually, and this is in meters, and work is actually in Newton meters, and we call that joules. Okay, so the unit for work is in joules, but it is really just Newton meters. All right, let's take a look at an easy example. Rudolph is pulling a toboggan and is exerting a force of 40 newtons, acting at 24 degrees to the ground. So if this is the object and Rudolph is tugging this, if this is the ground, wherever we draw that vector, could be lower, right at the bottom, doesn't really matter, as long as I know that this is 24 degrees. And this vector right here that's being tugged is 40 newtons. Now, if he pulls a toboggan 100 meters, how much work is done? Okay, so what we need to do is, this is the line of displacement because he's moving forward this way. I need to figure out if this is going 100 meters, I can put 100 meters here. I need to get the component of the force in the direction of displacement, and that is the projection, right? If I project this vector up here, which is the tug line, onto the line of displacement, and I multiply those two, that's how I calculate work. So I can just go here, and really what we're finding is the vector h down here, okay? Because it's not 100 meters, that's a different unit. Okay, and the magnitude of h is just 40 cos 24 degrees, which is a dot product. Okay, we learned that in the previous sections. So the magnitude of h equals 36.54. This is just h, the vector h. Now I need to find the work. So I can say the work is 36.54 times the displacement. So my work is 3654 joules. That's how much work is involved in tugging this toboggan. Okay, a little confusing maybe with the diagram. That 100 meters just tells us how far this is being tugged. It's not really part of the diagram that I'm interested in. Really, what I'm interested in this vector h. Okay, now continuing on to the cross product, application of a cross product, we can use the cross product to actually calculate area of a parallelogram. So recall the formula for a cross product. We can use either one of these. We're going to see an application of this version of the formula in the next example. But right now, if we have an area of a parallelogram, we have a parallelogram defined by two vectors. We have one vector like this, one vector like this, and we can form a parallelogram by continuing those two vectors. So all we have to do is find the magnitude of the cross product, and that tells us the area of a parallelogram. So that's a pretty easy thing to remember and to perform. So I'm just going to find the cross product of P cross Q here. And you can do it whatever way you want, memorizing formulas, setting up your cross like this, 5, 6, -1, 5, 3, -1, 2, 3, and then we could just do the 3 crosses, 5 times -1, and I continue on like that. So I'm just going to get right into the answer here because we know how to do the cross product. And there's my cross product. Now I have to find the magnitude of this, and just in case we're confused, this is -5 minus 18 is -23, 12 minus -2, that doesn't make any sense. Sorry, minus -1 is 11, +1. And finally is -3 minus 10 is -13. Okay, so I like doing it this way. If you want to do it the formula way, you can. But now I got to find the magnitude of P cross Q because that is the area of the parallelogram. Okay, so I put that all 23 squared, 11 squared, 13 squared, add them up, square root it, and I get 28.62 square units. Okay, and this is the area of that parallelogram. That's it. The cross product tells us that. And we can apply this to other shapes too. We can find the area of a triangle because it's just half of a parallelogram. So if we see, a triangle, we can imagine that it is actually a parallelogram, and we just divide the area by 2. So we can apply this concept to further examples. I'll show you a triangle next, and then we'll move on to something a little bit more complicated. Okay, so for the area of a triangle, I just gave it in a little different way over here. Here we're making a triangle, or the area of a triangle, using points, whereas the previous example, we were finding the area of a parallelogram given 2 vectors. We don't have any vectors here. So what do we have to do? If the formula is in vectors, we need to come up with some vectors. So if this is a triangle with A, B, and C, for instance, I don't need these points. I want to know 2 of these vectors, whatever they are, so I can calculate the parallelogram's area and then divide it by 2. So step 1, get some vectors. AB, AC. I can find AB pretty easily by subtracting. We know how to do that. And I can find AC doing the same. That's no big deal. Don't really got to show work there if you don't want to. And now I can apply the cross product. Let's change it up. So I'm going to do AB and AC, these guys. So -2, -1, 0, -2, -3, 3, 4, -3. Cross, cross, cross. Get rid of this for now. So AB cross AC is equal to -6 minus -3, 9. -4 minus 0, -4. And 0 and -8. Sorry, minus -8, so +8. And that's the cross product. Now I have to find the magnitude of the cross product. This squared plus this squared plus this squared, this is 161, and I have to find the square root of it to find the magnitude. So this would be the area of the parallelogram. So therefore, the area of the triangle in this problem is root 161 divided by 2, and I can change it into a decimal if I want, if I don't have to give exact values, and this is square units. Okay, so just a bit of a change here. We have some algebraic points, and we came up with 2 vectors, and then we did the cross product, divided it by 2. A few steps, but pretty straightforward. Okay, so another application of the cross product is torque. Torque is pretty useful in understanding, a car engine, to be honest, or most importantly, the rotation around a bolt. So this is just the cross product, and we can understand it using this formula as well, because when we are tightening something or loosening something, we require an angle applied at that force. So here's the first example. A 20 Newton force is applied at the end of a wrench that is 40 centimeters in length. The force is applied at an angle of 60 degrees to the wrench. Calculate the magnitude of the torque about the angle of the point of rotation. So if this is my point of rotation, I'm going to take my wrench and I'm just going to put it here. I'm not going to really attach it. And this is the radius of the wrench, right? And we know this is the wrench that is 40 centimeters. Move this over here. So this is 40 centimeters. I'm applying force in this direction. So the force F is right here. And I know that that is 20 newtons. This is angle theta. That's 60 degrees. So really my torque is just the cross product, but I really want to understand it in terms of these terms. And the main reason is because it's kind of geometric, right? I actually have the force of this vector, it's not really geometric. So I have my radius, which is 40 centimeters. I'm going to turn that into meters. I have because of that Newton meters. I have the 20 newtons right here and sine of the angle. And this equals 6.93 joules. Okay, so my torque in this case is 6.93 joules. And why is torque cross product? It's kind of cool actually, because I have a vector this way and a vector this way. And the force that's being applied into this bolt is actually perpendicular to those two forces, right? That's why we turn in this direction to make a screw go up or down. It is the perpendicular vector of the force being applied. Some really cool stuff with torque, you know, opening pickle jars. Why can weaker people open pickle jars? It's honestly because they naturally understand the angle in torque. So let's take a look at this sine value. This sine value, as sine gets closer to 90 degrees, it'll get closer to 1, right? From 0 gets closer to 1. So the torque increases as the angle of rotation increases. So if you're trying to apply the maximum amount of torque here, you should not do it at 60 degrees. You should do it at 90 degrees, perfectly down. And that's really key when you're, loosening bolts of a car tire. When you're on the side of the road loosening it, you really want to apply the force. The wrench is horizontal and you want to push directly towards the ground at a 90-degree angle. Another cool thing, how to increase your torque, is this radius right here. This 40 centimeter radius, as this radius goes up, the torque goes up. Well, this means if I want to increase my torque, I could just increase the length of my wrench. Okay, or, don't hold the wrench here. You want to hold it as far away as possible. And likewise, you can keep extending the length of that wrench and you have much more torque. And you want to have the maximum amount of torque. You want the longest wrench applied at the angle closest to 90 degrees. And that's how you get the most power. Hard to understand with a pickle jar, but if you're opening that pickle jar, you don't want to turn it from here. You want to turn it at 90 degrees. You should just go practice and work with that angle, and you'll be surprised at how much power you can exert if you actually adjust your angle. And that's it. That's applications of the dot and cross product.